All right, so let's think about the equilibrium condition of this model here. So there's kind of two different things that can be happening, and we're really relating to what's happening theoretically with what we're actually seeing in terms of the actual output in our economy. So if AE is greater than Y, so if the desired amount of expenditure is greater than the actual amount we see, so that means desired is greater than the actual. What's happening here is that inventories are starting to be depleted, right? People want to buy more than, if you want to think of it this way, than we kind of imagine them wanting to do. And so as people kind of buy more things, or however you want to think about AE being higher than Y, what's happening is that inventories are falling. We have to bring the stock from the back of the store to the front and order new stuff because people want to buy more than we thought they want to buy. And so what's going to happen is that inventory is falling, which means there's pressure on output to go higher. So think of that as actual output goes higher. So that's what's going to happen if AE is greater than Y. We can think of the opposite case. So if AE is greater than Y, there's pressure on Y to go up. If AE is less than Y, so if desired is less than actual, what's happening is that people maybe aren't, if you want to think of it this way again, people aren't buying as much as we thought they were going to buy, so we have all this extra inventory. Well, we don't need to order more, and we don't need to invest in any more inventory. So it's like our inventory is higher than we thought. Maybe it's lower than we thought here in terms of that downward. So it's higher than we thought. Well, this is going to cause actual output to go down because we're not going to invest in more inventory. And so our equilibrium condition, or when there's no kind of pressure on anything to change, is when our actual and our desired are the same thing. This is our equilibrium condition. Desired level of aggregate expenditure equals the actual amount that we see in our economy. So now let's go back to both our graph and a little bit of that algebra and think about what it means to invoke our equilibrium condition. All right, so our equilibrium condition we just talked about is AE being equal to Y. And so if you remember our example here, we had AE on the Y and Y on the x-axis conveniently. We had our AE function, which had an intercept, I think, about 105, had a slope of 0.8, and this was our AE function. If we think about what our equilibrium condition is, it's that this amount equals that amount. That's exactly a 45-degree line, right? Our equilibrium condition is essentially a 45-degree line. Because at every point along this condition, AE equals Y, just by definition, this 45-degree line. And so if we wanted to solve for equilibrium, we just have to see where this equilibrium condition crosses through this AE function, or in this AE function crosses through this equilibrium condition is probably a better way of thinking about this. So this is our equilibrium level of Y. Maybe I'll just call it Y1 or something for now. And so on this part of the graph, here the AE function is above Y, right? So the desired is above Y, and we talked about how that's going to cause upward pressure on output. So we're not in equilibrium anywhere over here. And then anywhere to this right-hand side, we had AE is less than Y. So there's kind of downward pressure on output because inventories were accumulating. And so this is graphically what our equilibrium condition or equilibrium looks like in this kind of demand driven model. We can also think about this mathematically, but in terms of algebra, in terms of how we get this y1. We do have a functional form here. We could solve for this. So let's think about our AE function in our example was equal to 105 plus 0.8 times y. With equilibrium, under equilibrium, y equals AE, which means that y equals 105 plus 0.8 y. Well, then we just need to solve for what this y equals. So we can say y minus 0.8 y equals 105. We can common factor the y out. 1 minus 0.8 equals 105. 0.2y equals 105. I'm just showing all the steps here. 105 divided by 0.2, which is the same as multiplying it by 5, which gives you 525. So this is 525. So if you wanted to mathematically or algebraically solve for this equilibrium where these two lines cross, we just invoke our equilibrium condition and solve for y here. Okay, so we know how to draw out this AE function with this example. We're going to have to make it a little bit more general. Instead of having these numbers, maybe we'll have a letter to indicate different possible numbers. Now we can invoke our equilibrium condition, which is this 45-degree line, and where AE function crosses this equilibrium condition is our equilibrium level of actual GDP or actual national income. If we want to solve for this, we just set our AE function equal to y, which is what we did right here, and we just solved for y, and we got 525 in this example. If we have numerical examples, we'll get numbers out of it, but if we just have letters, this will just be y will equal some expression. Let's be a little bit more general with our equilibrium now. Instead of actual numbers, let's just think of what it looks like algebraically. Equilibrium, I'm just going to put general in brackets. All right, so we have AE, maybe I'll underline that. AE equals C plus I. And we've decided this C equals A plus B times YD. And we've decided that investment for now, or we're deriving it here, is just equal to some constant I0. So what we did is we kind of plugged these into our AE function and simplified it a bit. AE equals A plus B times YD. This was consumption. Plus I0, and this was investment. So there's no taxes. So it says no taxes there. It's not one word. Sorry, it was a little close together. No taxes, if you can hopefully read that. Which means that YD equals just Y, right? Because YD is Y minus T, and this is equal to 0. All right, so now we have AE equals A plus B times Y plus I0. Well, what we can then do is collect the terms multiplied by Y and then collect the terms not multiplied by Y. What I mean by that, or how we, the language we'd use here is we'd collect autonomous aggregate expenditure and then have induced separately. And so AE equals A plus I0 plus B times Y, where this is autonomous aggregate expenditure. Last time that in our example it equaled 105 million or billion or whatever units we're working with, where this is induced aggregate expenditure. It's the amount of aggregate expenditure that depends on the level of national income. And what we're going to do is we're going to think about rewriting this, or kind of simplifying this, And so we're going to denote all the autonomous aggregate expenditure as just being equal to capital A. We're going to call the slope of the AE function Z. So this is the marginal propensity to spend. So if our national income went up by $1, this is how much of that dollar we'd increase our desired aggregate expenditure by. And this is the autonomous AE, right? In this case, it just equals A plus I0. In this case, in this really simple case, this marginal propensity to spend is going to be equal to B. So right now, it just seems like, oh, we're just changing B and calling it Z or Z. There is going to be a difference between Z and B as we kind of add parts of the model. So starting next week when we add trade, we're going to see that this Z is a little bit more complicated than just being this marginal propensity to consume, or B. Okay, so if we drew out our model here, maybe I should have given myself a little bit more space. Maybe I'll erase this and make it a little bit smaller, because then we can kind of talk about equilibrium all in this one slide, so to speak. So if you want to think graphically what's going on here, again, we have aggregate expenditure on the y and y on the x. Well, the intercept of our aggregate expenditure function, or capital A, is the amount of autonomous aggregate expenditure, so it's the intercept of our AE. And the slope of this AE function is Z, which again is just B right now, but it's going to change going forward. So it's useful to get used to this language now. And then we have this equilibrium condition, which is this 45-degree line where y equals AE. And so essentially, if we're solving for equilibrium, we want to solve for this point here. Well, here's our, maybe I'll specify that we're going to solve for equilibrium here. Y equals AE, which means y equals A plus Z times y. Now we're just solving for y minus zy, where z is between 0 and 1, equals A, or y equals A over 1 minus z. Well, here is our equilibrium. That's what this equals. And so, if we had numbers, and I asked you to solve for this equilibrium, what you could do is just plug in the aspects of capital A. You could just plug in little a plus I0 up here. You could divide it by 1 minus z, and here z is just equal to b, though it's going to change. And we'd be quickly able to solve for equilibrium national income. As we make the model more and more complicated, what this capital A represents and what this Z represents is going to change a bit. But again, the Z is going to represent the slope of the AE. It's just going to get a little bit more complicated. And the capital A is going to represent the intercept of the AE function. Right now it's just these two elements, but there's going to be more in terms of government purchases and things like that as we move forward.